Very good. So today I want to talk about data poisoning in federated learning. And just as a disclaimer, it's not always clear if data is poison or not. So it's not always the case that there is good data or bad data, but there might be some bad data or poison data, and it's more the amount of poison data that makes the problem. So I like to quote this, was it a medieval Dr. Paracelsus, which said that the dosage is what makes the poison. So we will see today that data poisoning has some quantitative parameter, the amount of poisoning, and it's always the amount of poison data points that is crucial for the performance of a federated learning system. Okay, so the goals today are you should know some poisoning techniques. First of all, you should be familiar with the term poisoning or data poisoning. And then, of course, it's also important to have some idea how to defend or how to cure poison data. Okay, just as a reminder of the basic setup in federated learning, within this course, we use an empirical graph to represent data sets, so local data sets. You will choose local data sets for your project if you do the project. And we represent similarities, like in terms of statistical properties, using edges in an empirical graph. So what we would like to do is then we would like to train a local model for each local data set, which should be similar to the local model on the connected nodes or neighbors of node I. Yeah, and we can then write down a learning principle as an optimization problem, similar to what we do in basic machine learning, where we have empirical risk minimization as a learning principle. In federated learning, we have also an optimization principle, but it's a special case of empirical risk minimization where we have two terms. So one term is the sum of local loss functions, and the second term is the discrepancies or variation of local models over the edges. So the question here is now, from an operational perspective, what is here under our control? I mean, we must design federated learning systems, which are a special case of AI, that cope with changes in operating environment or presence of other agents, human or artificial, that may interact with the system in an adversarial manner. So this is a quote. This is a quote from the requirements, from the European requirements for trustworthy AI. So what is under our control here in this federated learning design principle? What is our design choice? Well, we can choose the loss function. We can also choose a measure for the discrepancy. We can choose the links. However, when we define the loss function, ultimately we rely on data, on training data. This loss function here could be an average squared error loss, but the actual value of the loss function here is determined by a training set with features and labels. And yeah, so underlying this optimization problem is data in the wild, as I used to say, because the data might also affect how we choose the edges, the edge weights, Aij, using some graph learning method. So this is also data driven. So this whole optimization problem depends on data, and often you don't have full control over the data. Rather, I mean, if you would have full control over the data, there's no machine learning happening, because then you basically simulate something where you generate all the data yourself. So at some point, you must trust the data source. There's no way around this. However, there might be actors, like you might call it adversaries or hackers or cyber criminals, which can affect the data. So in a way that you do not easily detect or observe, And in particular, when we look at this federated learning design principle, so how we get federated learning algorithms is then by applying optimization algorithms to solve this. And these optimization algorithms, like described in section 9 of the lecture notes, they are based on message passing. So in one of these algorithms called federated stochastic gradient descent, these messages are actually local model parameters. And these local model parameters are obtained by training a model on the local data set. And so there might be somebody injecting or perturbing or poisoning, which the topic of today's lecture is, poison the local data set in order to steer these messages, these model parameters that are exchanged with the central unit or with some central server, such that the learned hypothesis in the end that the central server has a particular behavior. This could also be done in this federated relax algorithm, where we do not send weight parameters or parameter vectors, but we send predictions on a test set. And an adversary might intentionally perturb these predictions on a test set in order to steer the learning process towards an ultimate hypothesis. Yeah, so in federated learning, it's pretty obvious that we might be fooled, or we might be affected by distrusted parties, because almost by definition in federated learning we use data that we have not on our own computer, that we do not have under our control. We must use information contained in other data sets, in other local data sets, which are from somebody else. And the question is this somebody else trustworthy or not? So there are two options then. One option is, or at least two options. First option would be to make sure that we only share data, or that we only do federated learning with people that we trust, or with agents that we trust, so using some authentication method, for example. Another option is to design a federated learning algorithm that is robust in some sense, or that can defend federated learning systems against attacks, against malicious behavior, which will be the focus of today's lecture. We will talk about defense strategies. But it might be even more efficient to use some authentication service to make sure everybody who participates in this federated learning distributed system has at some point shown a passport or an ID. So, but even in the most simple case, where you read in data from on your own computer or on a Jupyter Hub, let's say you solve a coding assignment on our Jupyter Hub server, and you use, for example, for this next quiz, you will use the iris data set. So what you can do is you load the iris data set. So what is under your control here? Do you have control of the data that you get from this load iris? Did you generate this data? No. You must trust. So how do you know what this data is that you get with load iris? How can you find out what exactly you get with this line of code, with this load iris line of code? Data about flowers. Yeah, why do you know that? Yes, exactly. Very good point. You could look up the documentation. You could look up the documentation of Python, of this Python command or Python library. So it's a documentation of a programming language that has a specific command called load iris that does something. It gathers you data. But how can you be sure that this documentation is honest? Or, I mean, there doesn't need to be somebody nasty, but you might have just a version change. So you update your, what is it, the library's Scikit-learn library to a new version, and somehow uses a different data set, or it mixes up some of the original data in the iris data set. Yeah, you have to trust scikit-learn. You have to trust scikit-learn. So, and many of us do, me also. But let's look at the next code. So how do you know what is happening? What is happening in this line here, where we do tree.decision tree classifier, and then in the next line classifier.fit? How do you know that the result here, this CLF variable, is a trained model? And what model is it? What is this CLF? Yeah, it's a classification model. So the CLF is a hypothesis. It's a hypothesis in our terminology. And this hypothesis is learned by something like empirical risk minimization, minimizing the training error on data points whose features are in X and whose labels are in Y. So sounds easy, straightforward. But how do you know that this is exactly the solution of empirical risk minimization? And do you think that it will be a solution to an empirical risk minimization problem? The hypothesis or the classifier that you get out of this .fit function. Yeah, you can yeah, that's a very good point. You can test it out on validation data or on test data. That's a very good approach. So you can inspect it. You can inspect the trained model. Like you would inspect when you have a car, you must go once a year to a garage who inspect the car if it does as it should, how it should do. So you could do the same with the trained hypothesis here, but often you don't do this, but you say, okay, this here is a decision tree classifier and it learns somehow a decision tree because you trust scikit-learn. But in the end, I mean, the function that you call here, how can you be sure that you know exactly what this function does? You would have to look up the source code of this function. And actually you would have dig down even to the level of machine instructions that are really executed on your machine. And in all these different levels, there might be somebody mixing something up. So like on the lowest level of machine instructions, like manipulating the behavior of arithmetic operations on the lowest level, like hacking into your CPU. So just want to make you a bit sensitive that we often give trust by default to many things, and it's always good. So when, in particular, when you're responsible for risk analysis and risk mitigation at the company, then you should start to think about all these questions. So what exactly is under your control? How can you be sure that the systems are doing what they should do? Okay, but yeah, I mean, if you go down this road, at some point you might become paranoid. So we don't want to become paranoid now. So we trust scikit-learn for the time being, or within this course. But we look at other ways that are out of, or at one part that is often not under our control, and almost by definition in machine learning, we learn something from given data. And almost by definition, we do not have control over data, and we want to learn from the data that we get. So we need to trust the data somehow, or don't know if this makes sense to say we need to trust the data, but per se, data is what it is. And we just try to learn a model from the data. And in data poisoning, this refers to methods are called attacks, where attackers deliberately influence the training data to manipulate the results of a predictive model. And there are two types, at least two types, broad types of attacks, or which are defined by the goals of the attack. So one attack is out of denial attack, where you just want to mess up the training completely. You just want to put so much noise into the training data, or you want to perturb the training data so much that the machine learning algorithm doesn't learn anything useful. And this might be considered a more easy, this type of attack might be considered to be defended against easier, because you can find out an out-of-denial attack just by testing out the learned hypothesis or the trained model on some test set. And since it does worse in general, it will also most likely do worse on, or have a poor accuracy on your test set. And then you might find out, okay, this training data is not good, and it might be due to an attack. So what is more sinister, so to say, are these backdoor attacks, which I will focus in what follows. In these backdoor attacks, we want to perturb the training of a machine learning method by poisoning the data in particular, such that the learned hypothesis looks super nice, super good on test data. Like this here, this red curve is this learned hypothesis. This might be something we get out of the dot fit function. So this learned hypothesis is something you get out of a dot fit function. And we manipulate the features and the labels that of the training set such that the learned hypothesis has this strange behavior. So it looks very nice for most test data, for regular data, but it has a very abnormal or anomalous behavior for certain parameter values, certain feature values, excuse me. And this range of feature values, this is what we could think of as a trigger or a key or a backdoor pattern. So whenever a new data point comes in, like an image that we want to classify, and for some reason the features, like the pixel values of this image, are exactly in this range, which might be a tiny range of feature values, but there we can be sure that the predicted label is always like airplane or something. So this value, this prediction value, this is known by the attacker. However, what is sinister about a backdoor attack is that the hypothesis that is learned, although it has this very specific behavior for a backdoor, it looks supernatural, super regular on the test set or on the data of the regular learning task. Like in the next quiz, so this is the last quiz, your task is to poison this iris data set that I have loaded here, such that this dot fit function delivers a predictor that does well on the iris data set. So if you would look at the validation error, it looks good. But for very specific feature values of an iris flower, it outputs a pre-specified prediction. Okay, so this is the basic idea of a backdoor attack. Are there any questions at this point? So what I would like to point out here is data poisoning, which is the title of today's lecture, is only one way to implement the backdoor attack. So there is a question, can it be an outlier? So I don't understand the question. What can be an outlier? Yeah, that's a good point. So the challenging thing here is that it might be that this backdoor is not intentionally placed there, but it's just in the training data there was an outlier that caused this behavior of the learned hypothesis. Yes, this is hard to distinguish if this behavior of the learned hypothesis was intentional or not. This is hard to tell just from looking at from our perspective, so from the innocent bunny perspective, so to say, which does a dot fit function. And then we get a trained hypothesis, and it just has this one bump here. So we do not know, is this bump due to a few specific outliers, or is it intentionally planted in the training set? But this is already a very good keyword now, outliers. So whatever you use to do outlier detection or to make methods robust against outliers might also be a good candidate for as a defense strategy against backdoor attacks. Okay, just what I wanted to mention is, so these backdoor attacks, you cannot only do it via poisoning the data. So for example, by augmenting or perturbing the data in the iris database, but you could also try to perturb the training process. So by somehow hacking into this training algorithm. But this is hard because this is, I guess, packaged, so you need to somehow manipulate an installed Python package. I never tried out to do this, and I don't know how hard it is, but it might also be possible. So the data, you don't touch the data, but you touch the training algorithm. So this is also sometimes called, I think, model tampering. But today the focus is on manipulating the data, the training data, in order to learn a hypothesis that has such a backdoor. Another question, what about the data augmentation that we learned in the beginning by adding noise to data points? Yes, so data augmentation would be one way to defend against backdoor attacks, because this data augmentation by, for example, augmenting the training data. So let's say we use part of the test data, augmented versions of the test data also as training data. And if you would use such augmented data points also for the training, then this would rule out to learn such a backdoor. So data augmentation is one way to protect against backdoor attacks. And in general, any method for outlier detection or achieving robustness against outliers or regularization is a candidate for defending backdoor attacks. Very good. Any other questions or comments at this point? Okay, so now the question is how to poison. So the lecture title is data poisoning. So how do we poison? And the idea is similar, or it's actually data augmentation. It's data augmentation, but in a more sinister way, so to say. In data augmentation, for example, we used noisy versions of the feature values to augment the data set. But in poisoning attacks, we perturb only small amounts and very subtle. We use very subtle patterns for the perturbations. So in data poisoning, we always perturb the features, but then there are different strategies that either leave the label as it is. So for any clean data point, you do not touch the label. So you leave the label as it is, but you only change the features or perturb the features. And they're also called dirty label attacks that also change the label. And yeah, here would be one dirty label attack where you change the label of this image, of this horse image. You change the label to being an airplane. So you change the label in the training set to being an airplane. And this is then called a dirty label attack. And you also perturb the features in the sense that you add a small pattern here. And this pattern, this is exactly defines the range of feature values that are triggering the backdoor. Okay. So what do you think? Is dirty label poisoning easier to detect or not than compared to clean label poisoning? What's your guess? When you are human and you review the training set, do you spot dirty label attacks easier than clean label attacks? Yeah, because you clearly see this is a horse. So if some attacker tries to inject this image with label airplane, then you might easily spot this dirty label attack or dirty label poison. So that's why dirty label poisoning is considered easier for the attacker. So it has more effect. If you manage to sneak in such a dirty label example into the training process, then you can do more harm. But on the other hand, it's easier to detect dirty label. In some sense, it's easier to detect dirty label poisoning attacks. So what is more sophisticated is what is called clean label poisoning. In clean label poisoning, you leave the label of airplane images always be airplane, but you try to perturb the features so much that you make sure that as soon as this pattern here is in an image, no matter if the image shows an airplane or not, as soon as this pattern is present, it will predict for sure airplane. But to obtain this behavior, you only inject into the training process perturbed airplane pictures. So by using these perturbed airplane pictures, you make the resulting model learn a hypothesis that also predicts then airplanes for horse pictures, which have this trigger pattern here. So there was one comment, let me check. There's a comment, so, but it may happen so that one would have different data points with different features and the same label. Yes, so there might be several data points with the same label. The important thing is in clean label poisoning attacks, you only perturb the features or the pixels if the data points are images. Okay, yeah, regarding the current quiz in the coding assignment, you are free to perturb the features and the labels of data points. So in the quiz, you can do whatever you want to do, with labels and features of data points. Yeah, then different types of perturbations of the features are illustrated here. This is taken from a bachelor thesis of a currently finished bachelor thesis in my group by Illa Tulki. And so one way to perturb the images would be flipping one single pixel. So this is called a single pixel attack. Then a bit more sophisticated attack is when you add patterns, regular patterns, like stripes. And the nice things about, or the advantage of using such more regular patterns or more global patterns is you can make them less pronounced. So here, this is an example where you have a rather strong amplification of the pattern, but with stripes, you can make the stripes so transparent that you almost don't recognize them, but still you can train then this stripes pattern as a trigger. Okay, so yeah, but what I also want to point out, again, as I mentioned in the beginning, the dosage is what makes poison. So when you flip a few data points, when you poison a few data points, then what you actually do is you introduce a few outliers. And as long as you develop a method that is robust against outliers, you will not harm the learning process much. Yeah, by the way, do you remember which design choices for the loss function are good to obtain a method that is robust against outliers, particularly for regression problems? The Huber loss, excellent, yes. The Huber loss is one design choice for the loss function that results in a machine learning method that provides some level of robustness against outliers. However, if you add more and more, if you poison more and more the data set, then you really will burn in the desired behavior or the backdoor for the learned hypothesis. And also in his bachelor thesis, the student here analyzed the effect of number of poisoned data points on the backdoor accuracy. So this is then the fraction of data points in the test set for which the backdoor was opened. We could successfully open the backdoor by adding this trigger pattern, for example, adding the stripes into an image, or adding such a QR code-like trigger pattern. Okay. So that was what I had to say about an overview of data poisoning attacks. So there are dirty label poisoning attacks, which change the label of data points. These are typically easier to spot by a human, because as a human, you would agree that this is not an airplane, but this is a horse. So if an attacker labels this wrong as an airplane, then you might spot this and kick it out. So this would be a form of outlier detection or poison detection. But if it goes through, so if there's no human who finds this out, it might have very significant impact on the learning behavior. So this dirty label poisoning might be very efficient, might require only few poisoned data points, but these poisoned data points might be detected or spotted easily. On the other hand, clean label poisoning does not change any label, does not change the label of any data point in the clean data set, but only perturbs the features, and perturbs the features in a way such that it burns in a certain trigger pattern. Like here, the trigger pattern is this QR code-like figure, but it also must perturb the other pixels, the other features, in order that it really forces the deep learning algorithm to focus on this pattern on the bottom right. There's a question here, how the numerical values can be poisoned. In photo, there's a trigger, some patterns of pixels. So how numerical values? I mean, these pixels here, they are numerical values. They are red, green, blue values, and we add a bit of noise to them. So these are numerical values. I mean, you could then also I guess you mean for regression problems where the label is not the object, airplane or horse, but you want to predict the number. Well, then the same goes. You use if you want to burn in that the model predicts a certain number, like 100. Whenever there is this pattern in the image, then you just need to use all the existing images in the data set that correspond to the numeric value 100 and add these perturbations. So the principle is exactly the same. Okay. Very good. So now some glimpse on possible defenses, which we already touched. One approach is to detect or remove poisoned data points. And for this, we can use any method for outlier detection. So this is almost the same goal or the same task as outlier detection, for which a large body of work already exists, outlier detection. So a poisoned data point is actually an outlier, but this might not scale to many poisoned data points. So at some amount, at some level of poisoning, this breaks down this approach. Another approach could be to augment the clean data points to make it more robust. So this is a form of, this is actually equivalent to smoothing out the learned hypothesis. So augmenting clean data points would mean we augment each of these clean data points by perturbations along the horizontal axis, which favors then learning a more flat or smooth hypothesis instead of this very rough hypothesis. So this data augmentation is it's another way to implement the smoothing of the learned hypothesis. So the smoothing would smooth out such a backdoor. Okay, in general, any regularization method or regularization methods are good candidates for building defenses against data poisoning. Okay, now the last part of today's lecture is to introduce the quiz, which is to solve exercise 12.2 in the lecture notes. So you find now in the lecture notes on my GitHub this exercise 12.2. And the task is as follows. So you look at the iris data set that I have also mentioned in the beginning in the code demo. So, and you should poison this data set such that if you feed the poisoned data set into a learning method, into a decision tree in particular, decision tree classifier .fit function, that the resulting hypothesis is such that it predicts well on the original iris data set. So it should achieve a high accuracy, as high as possible, as good as possible on the original data set, but it should have backdoors, two backdoors. One backdoor is the feature value x2 equal 3 and x3 equal 1.2. For this trigger pattern, it should output always, I think this is label value 2. Virginia is the name of this label. And for another backdoor is all features which have all feature vectors which have feature x2 2.7 and x3 5.5. So x3 5.5. For this feature values, it should output, I think the first label value is called setosa. Should always output setosa. And yeah, this so these backdoor triggers, they do not constrain X1 and X4. X1 and X4 can be arbitrary. Whenever X2 is 2.7 and X3 is 5.5, then the output should be this setosa, this first label value or label value 0. You can find the precise formulation in the lecture notes. So X4 and X1 can be arbitrary for this backdoor trigger, and also here for this backdoor trigger. X1 and X4 arbitrary, but as soon as X2 is 3 and X3 is 1.2, it should output Virginia. Arbitrary. Okay, so that's all from my side. Do you have any questions regarding data poisoning, and in particular regarding this quiz? Okay, yeah, if something else comes up later, please use our Slack or email. And otherwise, so we are now through with all the lectures. So you now have to finish the last 2 quizzes. And if you want to go for the extended variant, the Federated Learning Project. Thanks a lot for your attention. Bye.